What is the invisible force that orchestrates the dance of the planets and the fall of an apple? Are the laws that govern a cannonball's flight the same ones that command the tides? What if the solid reality we perceive is built on a foundation of uncertainty and probability? And how can the universe be both a predictable clockwork machine and a realm of spooky action at a distance? Join me, my friends, as we explore these profound questions and journey through the history of humanity's quest to understand the cosmos in this new episode from the Human Odyssey series from English Plus Podcast. I'm your host, Danny, and this is the story of physics from Newton's apple to Einstein's universe and the quantum realm. Okay, let's start with our first part, the clockwork universe. Our story begins not with a bang, but with a fall. The year is 1666, a time of plague and superstition. A young man named Isaac Newton, a student at Cambridge University, has retreated to the quiet solitude of his family's farm. The world outside is in turmoil, but here, in the gentle English countryside, an idea is about to be born that will change the course of human history. The story, as it is often told, is a simple one. Newton is sitting under an apple tree contemplating the mysteries of the universe when an apple falls from a branch and lands on the ground. It's a mundane event, something that has happened countless times before. But for Newton, this simple act of falling triggers a cascade of questions. Why did the apple fall down, and not sideways or even up? What is this invisible force that pulls everything towards the center of the earth? And in a leap of imaginative genius, he wonders, does this same force extend beyond the Earth, to the moon and the stars? This was the spark, the genesis of a revolution. Newton's genius was not just in asking these questions, but in pursuing the answers with a relentless mathematical rigor. He spent the next 2 decades of his life developing a new kind of mathematics, calculus, to describe the way things move. He formulated his 3 laws of motion, which are as elegant as they are powerful. The first law, the law of inertia, tells us that an object in motion stays in motion unless acted upon by an external force. The second law tells us that the force acting on an object is equal to its mass times its acceleration. And the third law, the law of action and reaction, tells us that for every action, there's an equal and opposite reaction. These laws combined with his law of universal gravitation, which states that every particle in the universe attracts every other particle with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between their centers, formed the foundation of what we now call classical mechanics. Newton had, in essence, written the rulebook for the universe. He had shown that the same laws that govern the falling of an apple also govern the orbits of the planets, the tides of the oceans, and the flight of a cannonball. The universe, in Newton's view, was a grand, intricate machine, a clockwork universe, wound up by a divine hand and left to tick away in perfect, predictable harmony. For the next 2 centuries, Newton's ideas reigned supreme. Scientists used his laws to predict the motion of celestial bodies with astonishing accuracy, to design new machines and technologies, and to unravel the secrets of the natural world. It seemed as though humanity was on the verge of a complete understanding of the universe. The future, it was believed, could be predicted with absolute certainty if only one knew the initial conditions of every particle in the universe. The French mathematician Pierre-Simon Laplace famously declared that an intellect which at a certain moment would know all forces that set nature in motion and all positions of all items of which nature is composed, if this intellect were also vast enough to submit these data to analysis, it would embrace in a single formula the movements of the greatest bodies of the universe and those of the tiniest atoms. For such an intellect, nothing would be uncertain, and the future, just like the past, would be present before its eyes. Well, this was the dream of the classical world, a world of order, predictability, and certainty. But as the 19th century drew to a close, a few stubborn clouds began to appear on the horizon. Tiny cracks in the magnificent edifice of Newtonian physics that would eventually lead to its downfall and to the birth of a new and far stranger understanding of the universe. Now let's talk about these cracks in the edifice. The 19th century was a time of immense scientific and technological progress. The Industrial Revolution was in full swing, powered by the new science of thermodynamics, the study of heat and energy. Scientists like James Maxwell were unraveling the mysteries of electricity and magnetism, showing them to be two sides of the same coin, a unified force called electromagnetism. Maxwell's equations, a set of four elegant mathematical expressions, described how electric and magnetic fields are generated and altered by each other and by charges and currents. They predicted the existence of electromagnetic waves, which travel at the speed of light, and in doing so, they revealed that light itself is an electromagnetic wave. Now, this was a stunning achievement, a unification of three seemingly disparate phenomena: electricity, magnetism, and light into a single coherent theory. It was another triumph for the classical worldview, another testament to the power of mathematics to describe the fundamental workings of nature. But as scientists continued to probe the nature of light and heat, they began to encounter a series of puzzles that defied explanation within the framework of classical physics. One of the most vexing of these puzzles was the so-called ultraviolet catastrophe. According to classical physics, a hot object, like a piece of iron heated in a furnace, should emit electromagnetic radiation at all frequencies. And as the frequency of the radiation increases, the intensity of the radiation should also increase without bound. This meant that a hot object should emit an infinite amount of energy at high frequencies in the ultraviolet part of the spectrum. But this is not what was observed. In reality, the intensity of the radiation reached a peak at a certain frequency and then fell off to zero at higher frequencies. Classical physics was predicting an absurdity, a clear contradiction with experimental evidence. Another puzzle was the photoelectric effect, the observation that when light shines on a metal surface, it can knock electrons loose from the atoms in the metal. The strange thing about the photoelectric effect was that the energy of the ejected electrons did not depend on the intensity of the light, but on its frequency. A faint blue light could eject electrons with more energy than a bright red light. This made no sense from a classical perspective. If light were a wave, as Maxwell's theory suggested, then a more intense wave should have more energy, and should therefore eject electrons with more energy. These were just two of the many cracks that were beginning to appear in the classical edifice. The world of physics was in a state of crisis. The old theories, which has served so well for so long, were beginning to fail. A new way of thinking was needed, a radical departure from the classical worldview. And as the 20th century dawned, two young iconoclastic thinkers would emerge to provide it. One was a German physicist named Max Planck, and the other was a patent clerk in Switzerland named Albert Einstein. And that brings us to the quantum leap. The first shot in the revolution was fired by Max Planck, a reluctant revolutionary, if there ever was one. Planck had been working on the problem of the ultraviolet catastrophe for years, and in 1900, he came up with a desperate solution. He proposed that energy is not continuous as classical physics assumed, but is instead emitted and absorbed in discrete packets, which he called quanta. The energy of each quantum, he said, is proportional to the frequency of the radiation. This was a radical idea, a complete break with the classical tradition. Planck himself was not entirely comfortable with it. He saw it as a mathematical trick, a way to make the equations work rather than a description of physical reality. But the idea worked. It perfectly explained the observed spectrum of radiation from hot objects, and it resolved the ultraviolet catastrophe. The age of quantum physics had begun. 5 years later, in 1905, a young Albert Einstein, working in almost complete isolation from the scientific community, took Planck's idea one step further. He proposed that light itself is not a continuous wave, but is made up of a stream of discrete particles, which we now call photons. The energy of each photon, he said, is proportional to its frequency. This was an even more radical idea than Planck's. It seemed to contradict a century of evidence that light is a wave, but it explained the photoelectric effect with beautiful simplicity. The energy of the ejected electrons depend on the frequency of the light because each electron is kicked out by a single photon, and the energy of that photon is determined by its frequency. A more intense light simply means more photons, not more energetic photons. Einstein's paper on the photoelectric effect was one of 4 groundbreaking papers he published in his miracle year of 1905. The other 3 papers laid the foundation for his theory of special relativity, which we will come to in a moment. But it was his work on the photoelectric effect that would earn him the Nobel Prize in Physics, and it was his bold embrace of Planck's quantum hypothesis that would pave the way for a new generation of physicists to explore the strange and wonderful world of the quantum. The next few decades were a whirlwind of discovery. In 1911, Ernest Rutherford, a physicist from New Zealand, discovered the atomic nucleus, a tiny, dense, positively charged core at the center of the atom. This led to the development of the planetary model of the atom, with electrons orbiting the nucleus like planets orbiting the sun. But this model had a fatal flaw. According to classical physics, an orbiting electron is an accelerating charge, and an accelerating charge should radiate energy and spiral into the nucleus. The atom, in other words, should be unstable. And it was a young Danish physicist named Niels Bohr who came to the rescue. In 1913, he proposed a new model of the atom, one that incorporated the ideas of quantum mechanics. He suggested that electrons can only exist in certain discrete orbits around the nucleus, each with a specific energy level. An electron can jump from a higher energy orbit to a lower one, emitting a photon of light with a specific frequency in the process. Or it can absorb a photon and jump to a higher energy orbit, but it cannot exist in between orbits. Bohr's model was a strange hybrid of classical and quantum ideas, but it was remarkably successful. It explained the stability of atoms, and it accurately predicted the spectrum of light emitted by hydrogen, the simplest atom. But it was still not a complete theory. It didn't work for more complex atoms, and it couldn't explain why some spectral lines were brighter than others. The final and most radical break with the classical tradition came in the mid-1920s with the development of a new and more powerful version of quantum mechanics, a theory that would challenge our most fundamental intuitions about the nature of reality. It was a collaborative effort, a product of the brilliant minds of a new generation of physicists, including Werner Heisenberg, Erwin Schrödinger, and Paul Dirac. Heisenberg, a young German physicist, developed a version of the theory called matrix mechanics, which described the properties of atoms in terms of mathematical objects called matrices. Schrödinger, an Austrian physicist, developed a different version of the theory called wave mechanics, which described the behavior of electrons in terms of a mathematical object called a wave function. The wave function, Schrödinger said, represents the probability of finding the electron at a particular point in space. These two theories, which at first seemed so different, were soon shown to be mathematically equivalent. They were two different ways of looking at the same underlying reality. And that reality was a strange one indeed. In the quantum world, particles like electrons can behave like waves, and waves can behave like particles. They can be in multiple places at once, and their properties, like their position and momentum, are not well defined until they are measured. This is the essence of Heisenberg's famous uncertainty principle, which states that the more precisely you know the position of a particle, the less precisely you can know its momentum, and vice versa. The uncertainty principle is not a statement about the limitations of our measuring instruments. It is a fundamental property of nature. It tells us that there is a built-in fuzziness in reality at the quantum level, a fundamental limit to what we can know about the world. Another strange feature of quantum mechanics is the phenomenon of entanglement. Two quantum particles can be linked in such a way that their fates are intertwined, no matter how far apart they are. If you measure the property of one particle, you instantly know the property of the other, even if it is on the other side of the universe. Einstein famously called this spooky action at a distance, and he was deeply troubled by it. He believed that quantum mechanics was incomplete, that there must be some hidden variables that were not being accounted for. But experiment after experiment has confirmed the predictions of quantum mechanics, no matter how strange they may seem. The quantum world is not a world of certainty and predictability like the clockwork universe of Newton. It is a world of probabilities and possibilities, a world where the act of observation can change the reality being observed. It is a world that is, in many ways, beyond our ability to fully comprehend. And yet, it is the world that we live in, the world that underlies all of physical reality. And now let's talk about the fabric of spacetime. Now, while the quantum revolution was raging, another equally profound revolution was taking place. A revolution in our understanding of space, time, and gravity. And at the heart of this revolution was the same man who had kicked off the quantum revolution, Albert Einstein. In his miracle year of 1905, Einstein had published his theory of special relativity, a theory that dealt with the laws of physics in the absence of gravity. The theory was based on two simple but radical postulates. The first is that the laws of physics are the same for all observers who are in uniform motion. This means that there is no absolute frame of reference, no privileged position in the universe from which to observe the laws of nature. The second postulate is that the speed of light in a vacuum is the same for all observers, regardless of their motion or the motion of the source of the light. These two postulates have some mind-bending consequences. They imply that space and time are not absolute, as Newton had believed, but are relative to the observer. A moving clock will tick more slowly than a stationary clock, a phenomenon known as time dilation. A moving object will appear shorter in the direction of its motion, a phenomenon known as length contradiction. And mass and energy are two sides of the same coin, related by the most famous equation in all of physics, E equals mc squared. Special relativity was a stunning achievement, a complete overhaul of our understanding of space and time. But it was incomplete. It did not account for gravity, and it did not apply to observers who were accelerating. Einstein spent the next 10 years of his life working on a more general theory of relativity, one that would incorporate gravity and would apply to all observers regardless of their motion. The result, which he published in 1915, was a masterpiece of scientific thought, a theory of gravity that was as beautiful as it was profound. In his general theory of relativity, Einstein proposed that gravity is not a force, as Newton had believed, but is a consequence of the curvature of space-time. Massive objects, he said, warp the fabric of space-time around them, and this warping is what we experience as gravity. Imagine a bowling ball placed on a stretched rubber sheet. The bowling ball creates a dip in the sheet, and if you roll a marble nearby, it will be deflected by the dip and will circle around the bowling ball as if it were being pulled by an invisible force. This is a crude analogy, of course, but it captures the essence of Einstein's idea. Planets orbit the sun not because the sun is pulling on them with a force, but because they're following the straightest possible path through the curved spacetime created by the sun's mass. General relativity was a radical departure from Newtonian gravity, and it made a number of predictions that were different from those of Newton's theory. One of these predictions was that light from a distant star should be bent by the gravity of the sun. In 1919, a British astronomer named Arthur Eddington led an expedition to observe a solar eclipse, and he confirmed Einstein's prediction. The light from a distant star was indeed bent by the sun's gravity by exactly the amount that Einstein's theory had predicted. It was a stunning confirmation of a revolutionary new theory, and it made Einstein an international celebrity overnight. He had, in the words of the London Times, overthrown the Newtonian conception of the universe. General relativity has had a profound impact on our understanding of the cosmos. It has led to the prediction of black holes, regions of space-time where gravity is so strong that nothing, not even light, can escape. It has led to the development of the Big Bang theory, the idea that the universe began in a hot, dense state and has been expanding and cooling ever since. And it has led to the discovery of gravitational waves, ripples in the fabric of space-time that are created by the most violent events in the universe, such as the collision of two black holes. The detection of gravitational waves in 2015, a century after Einstein had first predicted their existence, was a triumphant confirmation of his theory, and it opened up a new window on the universe, a new way to observe the cosmos and to test the limits of our understanding. And that, my friends, brings us to the last part of today's story, the story of physics, the unfinished symphony. And so we find ourselves at the end of our story, or at least at the end of this chapter of our story. We have journeyed from the clockwork universe of Newton to the probabilistic world of the quantum and the curved space-time of Einstein. We have seen how our understanding of the universe had been transformed by a series of brilliant minds, daring ideas, and groundbreaking discoveries. And yet, for all our progress, we are still far from a complete understanding of the universe. The two great pillars of modern physics, general relativity and quantum mechanics, are, in many ways, incompatible. General relativity describes the world of the very large, the world of stars and galaxies and the expanding universe. Quantum mechanics describes the world of the very small, the world of atoms and particles and the fundamental forces of nature. Both theories have been tested to incredible precision, and both have been found to be remarkably accurate in their respective domains. But they cannot both be right, at least not in their current form. They are based on different mathematical principles, and they give different answers when they are applied to the same problem, such as the description of a black hole or the first moments of the universe after the Big Bang. The quest for a unified theory, a theory that can reconcile general relativity and quantum mechanics, is the great unfinished symphony of modern physics. It is the holy grail of theoretical physics, a prize that has eluded some of the greatest minds of the past century, including Einstein himself. There are a number of candidate theories, each with its own strengths and weaknesses. String theory, for example, proposes that the fundamental constituents of the universe are not point-like particles, but tiny vibrating strings of energy. Different vibrations of these strings correspond to different particles, and the interactions between these strings give rise to the forces of nature, including gravity. Another candidate theory is loop quantum gravity, which proposes that space-time itself is not continuous, but is made up of discrete quantum units. These units are woven together to form a spin network, and the geometry of this network gives rise to the curvature of space-time that we experience as gravity. These are just two of the many ideas that are being explored by physicists today. It is a long and difficult road, but there is no guarantee that we will ever reach the end of it. But the quest for a unified theory is not just about finding a set of equations that can describe the universe. It is about something much deeper. It is about understanding our place in the cosmos, about answering the most fundamental questions of existence. Where did we come from? What are we made of? And what is our ultimate destiny? And so, my friends, the Human Odyssey continues. The story of physics is a story of our relentless curiosity, our insatiable desire to understand the world around us. It is a story of our ability to imagine new worlds, to create new languages, and to push the boundaries of human knowledge. It is a story that is still being written, a story with no end in sight, and that, perhaps, is the most beautiful thing of all. Thank you very much for listening. That was our very first episode from our new series, The Human Odyssey. My goal is to produce 2 new episodes every week, so be sure to check them out. The next one is about the story of biology. You don't want to miss that. And with that, we come to the end of our episode. Again, thank you very much for listening. I'm Danny. You've been listening to English Plus Podcast. Remember, never stop learning. I will see you next time.